Thank you very much for the introduction, and I'm very happy to be here with you today. The topic of the presentation, as was mentioned, is about flood mitigation and how AI can be used for that. So it's a slightly different topic than construction, but my philosophy is that if you want to build new things first, you better understand how the existing things perform in floods. And for that, that's the focus of this presentation. We are looking at how the built environment responds to flood and whether there are technologies that we can use to better understand and communicate the risk of floods in the existing built environment before we even build new things. So this work is work from my PhD student, Bahareh Alizadeh, and I'm presenting on behalf of her. If you have any difficult questions, feel free to contact her. Otherwise, I'll be happy to answer your questions at the end of the session. But before I start about the methodology, just a quick introduction as to why floods are important. So some statistics from the US. In the United States, 90% of all disasters involve some sort of a flood, and almost all counties and jurisdictions in the country are prone to flood risk. And this is quite interesting because when you think of the United States, you might think that there are some areas that are completely dry and may not have flood risk, but actually climate is changing, and that's why the majority of the country is now exposed to flood risk. In the past 20 years, 2 decades, we had 5,000 flood events, give or take a few, and that has caused the life of about 2,000 people, and that's just in addition to the people who get injured and lose property and have to go through a lot of rebuild and recovery efforts as a result of these floods. And there is research that shows in the next 10 years, the economic cost of flooding will be tripled in the country. And what makes this even more challenging is that flood patterns are changing. Like I said, the areas of the country or the areas of the world that were not exposed to floods are going to be exposed to flood risks simply because we have asymmetric population growth and migration, we have deforestation, we have climate change, rising sea levels. So there are so many factors that will play a dominoes effect when it comes to increasing the flood risk in many parts of the world. Now, if you think about flood response, there are a lot of different modalities of data and information that authorities and general public may need in order to be able to successfully respond to a flood event, but perhaps one of the most important ones is knowing how much flood exists in an area, particularly in a residential neighborhood, in an area with a lot of population, because first of all, you have to be able to reach out to that population after a flood event. But second, you have to be able to kind of provide resources to those who get stuck there. You might want to provide debris cleanup resources, send municipality resources there. So you need to know where floods exist. And this is not something new. People have been trying to drive over flooded waters or walk simply out of their house and get to the shelter, assuming that there is no flood in their neighborhoods, just to know that in a few feet or a few meters ahead of where they are, they get stuck in the water. And in the state of Texas, where I come from, there is statistics from the Texas General Land Office that shows that 75% of those who lose their lives in flood events lose their lives simply because they underestimate the depth of flood water in their neighborhood. So this is kind of the focus of the project. We wanted to provide a more reasonable and an accessible methodology and technology for people to understand the depth of flood water in their surroundings. Now, when it comes, of course, to understanding the depth of floodwater, this is not something new. Most of you have seen flood gauges close to where you live. So these are traditional methods of measuring how much flood exists in a neighborhood. We also have water level sensors. Of course, these are good devices, but they come in different forms and shapes, and they're very difficult to access if you are stuck in your home. You can't really see where the flood gauge is. And of course, their coverage area is limited. They just measure where the flood is in that particular location, and then therefore you have to interpolate or extrapolate the data you get from these devices. And of course, then that means you have to rely on hydrological models, terrain models, and all sorts of other mathematical assumptions to get from one data point to close to where you live, which means you're adding to the error of measurement as you go through this process. And of course, another challenge with these devices is that there is limited time, there is a major effort for installing them, calibrating them, and maintaining them, and they easily get damaged, especially the traditional flood gauges like you see in these examples on the right side of the slide. Now, more advanced techniques include satellite imagery, aerial imagery, drones, as we speak, are being used in flood response increasingly. Well, these are good devices. The challenge is that the general public doesn't have access to this data in real time. So yes, these are good for planning purposes and thinking about future events and how we can prevent them. But at the moment when the people need that information, it's very difficult to get that information. And specific to satellite imagery, there is a challenge when it comes to urban areas because these imagery have been shown to be less accurate, especially when you have subtle changes in the surface texture. Like if you go from concrete to asphalt and to paved surfaces and to gravel, these subtle variations are not easily captured by satellite imagery. So satellite imagery is mostly used for rural areas as opposed to urban areas. That is the focus of this study. So in the US, the most common way of kind of documenting the flood depth is using flood gauges. There are less than 10,000 of them, roughly around 9,500 of these flood gauges across the country. These are operated by the US Geological Survey, or USGS. So obviously the distribution is not uniform. You see in some parts of the country towards the east, we have more of them. In the center, there are very few, and then on the west coast, we have some. But if you kind of divide the area of the United States by 9,500, you have one of these flood gauges roughly for every 400 square miles of land, which is like very, very few, considering that we are talking about residential neighborhoods and road network that are much higher spatial resolution compared to one gauge per 400 square miles. So in this research, what we wanted to do was to kind of use another type of existing urban landmark that is easily accessible and understandable and recognizable by everybody as a measurement benchmark for flood gauges. We didn't want to install new sensors. Obviously, that will take forever, and it requires a lot of time for installation and maintenance. So we thought maybe we can use something else that everybody can relate to, and that would be traffic signs. And we have traffic signs all over the country, all over the world. Most of the countries in North America and Western Europe and Asia, these signs are standardized, meaning they have shapes that, or colors and dimensions that everybody is familiar with. You guys have all passed your driving tests, so you have seen these manuals that basically show you what stop sign is, what yield sign is, bicycle passing, and all those things. So we don't know how many of these signs exist for obvious purposes. We don't know exactly where they are because police is interested in issuing tickets as you violate the stop sign, so they don't really tell you where these signs are in many parts of the world. But there are studies out there that shows that, for example, in the US, this study by Boeing in 2018, they found that for every 1 square kilometer of residential neighborhoods, we have about 50 intersections. And if you imagine in some intersections, we have 1 stop sign, 2 stop signs, 3 or 4, these are a lot of stop signs. So we focused on stop signs in this study, and of course, this can be scaled to other types of traffic signs as well. And the maps on the bottom right is just a comparison of how many stop signs we have on the far right. The top one is Philadelphia, and the bottom one is Bay Area, San Francisco Bay Area. And the maps next to them show how many flood gauges we have in those areas. So for example, if you look at Philadelphia on the far right, you see the blue and green dots are all the stop signs we have, 2-way or 4-way stop signs, versus these limited number of flood gauges. No flood gauge in the Bay Area, San Francisco Bay Area, versus these many stop signs in San Francisco Bay Area. So if you can just get readings of flood depth for each of these stop signs, we'll have a very high spatial resolution map of flood. Now, surprisingly, the methodology is not really that difficult. So knowing that the sign itself, the octagonal shape of the sign, is standardized, meaning it has a dimension that doesn't change regardless of where you live, then we can detect that sign, measure the height of the sign in pixels. We know that these signs are 30 inches in most residential areas and 36 inches in most highways. So then you can establish a ratio between inches and pixels, and then you can detect the pole underneath the sign, and therefore you can use that same ratio to find out the length of the pole. Now, if you have a picture of that stop sign before the flood, like the one on the left, and after the flood, like the one on the right, and you can measure the length of the pole in 2 cases, the difference of the length of the pole is how much water you have in that area. So basically DW, the depth of water, is the difference between P, which is the length of the pole after flood, and P prime, which is the total length of the pole when there was no water in that area. So if you can do this in real time in fast speed for many stop signs, then you will have a high spatial resolution map of floodwater depth. Now, of course, 1 stop sign photo is not enough, 2 stop sign photo is not enough, and perhaps 100 or 200 is not enough. The more you have, the better. So what we did in this project was that we also created a crowdsourcing application called BluePix. There is a link to that application. I'll show that to you in a moment, but also there's a QR code. So essentially the way this app works is that everybody can just go on the app on their mobile devices and take a photo of a submerged stop sign. And if they have time, they can pair that photo on Google Street View with the same stop sign photo before the flood, or they can leave the pairing process to somebody else. It's a crowdsourcing application. So he can upload a photo of a submerged stop sign and just disappear, and then I can go later as another citizen and find that photo and then pair it with the photo of the pre-flood stop sign. So then once we have these post-flood and pre-flood pairs, we run our detection model, find the stop sign and the pole length, and then we do the subtraction to find the depth of floodwater in that location, and then we show that information on the map. So the idea here is that as more citizens participate in this citizen science experience, you will have a higher spatial resolution map. So let me just show you an interface of this app. This is live as we speak. So all these blue pins are paired stop sign photos. And if you notice, there are a couple of yellow pins that are yet to be paired. So we have a post-flood photo of a submerged stop sign, but nobody has paired that with a pre-flood photo yet. So if you click on any of these pins, if this works, so you basically see a photo that was uploaded by somebody. This is a stop sign in North Dakota, and the stop sign is submerged. There is a flood height that was calculated by the AI model. It's displayed there, 28 inches. And you basically can see the same stop sign in a pre-flood situation. This was taken from Google Street View by that same person or somebody else who paired the photo. So you get kind of an idea as to how much water existed in that area. So of course, this is a great tool for real-time flood depth communication, but also for kind of historical documentation of how much water existed in that neighborhood, because seeing is believing. If somebody sees that stop sign that they see on a daily basis as they drive to work or come back from work was under that much water, next time they will pay more attention when there is a flood in the area. So clearly this map is still not complete. We are increasing the number of photos by reaching out to more communities and people. For some areas like Houston area right here at the bottom, we have some more photos because of Hurricane Harvey and the more frequent floods. For some areas of the country, we have less photos because floods are not that frequent in those areas. Okay, so let's go back. All right, so the backbone of the model is basically a YOLO version 4. YOLO stands for you only look once. Some of you may be familiar with that. It's a convolutional neural network object detection model. We specifically picked YOLO version 4 because of the architecture it has. So it has basically the backbone is a darknet 53. The neck is a spatial pyramid pooling and a path aggregation network. But without really going into the details of these networks, what happens is that this architecture increases the learning capacity of the neural network because it allows multiple levels of detectors at different resolutions of the image to extract global and local features of the image and then aggregate them at the end to give you a very complete view of what's going on in that figure. So specifically for our problem, because we have stop signs that might be very small as when you compare them to the larger view of the image, or you may have poles that are very narrow and difficult to see. This architecture works best because it allows different levels of detector to kind of analyze the image for you. Our model, like I said, is YOLO version 4. This model is pre-trained on COCO dataset, 2017 version, but we also retrained and fine-tuned the model on our own test training dataset. We had about 800 photos of stop signs. And then we tested the model on 147 photos of stop signs. And as I show you later, we also tested the model in a case study that was presented in this paper. So there are some challenging cases. Some of them are depicted here. For example, if there are more than one stop sign in a photo, of course the model tries to detect all of them. And in these cases, although they're rare, what we do is that we'll pick the sign that is closest to the camera. So the largest bounding box is picked for further analysis. And then another issue, of course, with water, just like any other reflective surface, like a mirror, is that parts of the objects are reflected in the water. So you may get this blurry, wavy kind of thing from the bottom of the water, which shows some part of the pole or the stop sign. and the model might get confused. These are very difficult problems, even in computer vision domain, but the way we approach it, at least for a limited scope of problem, was that we added these reflection cases, but we didn't label the reflection part, so the model learns that those parts are not necessary to learn from. The case study we focused on in this paper was on 11 photos that we were able to find from the 2021 Pacific Northwest floods. If you're familiar, this series of floods happened in the US state of Washington, where Seattle is, and the Canadian province of British Columbia, where Vancouver is located. So these photos were taken around the same time from those floods. We had 3 photos from the state of Washington. I'm showing you here the longitude, latitude, and the location of these photos. And in each case, we were able to collect the post-flood photo on the left side and then pair it using the longitude and latitude with the pre-flood photo on Google Street View. And the next slide shows the 8 images that we were able to collect from the British Columbia side of things. So again, post-flood and pre-flood and location of these images. This table shows a summary of how our model performed when it comes to detection or prediction of estimation of floodwater depth. So essentially, you can look at the very last column. That's the error in the flood depth estimation. And roughly, we have a mean average error of less than 7 inches when it came to predicting the flood depth. In some cases, like image ID number 6, we had a large error of about 35 inches, and that's a very specific case where the stop sign was backward, meaning the model couldn't really see the stop and the red shape. So we had a few of those cases in our training set. I think the model was not really learning from those cases. So there, except for those few exceptions, the model really performs well, 2 inches, 3 inches, less than 1 inch of error in some cases. Of course, this is a machine learning problem, AI problem, so the more data you have, the better the model will perform. And just to wrap things up, I want to acknowledge the support of our project sponsor, the National Oceanic and Atmospheric Administration under the Sea Grant program. And if you have any questions, feel free to reach out to me or my students, and we'll be happy to answer your questions. Thank you.